Okay, my name is Predrag. I'm the third year PhD student at the University of Copenhagen. And today I will talk about some statistics for nonlinear stochastic differential equations. And I will turn to first order and second order stochastic differential equations. And mostly this is what I've been doing for my PhD. And this is done under supervision of Professor Susanne Wittelsman and Adeline Sampson. Okay, and also I just want to point out that this work is funded by Marie Curie grant from EU, and it's part of a bigger project called EPOC. We are 15 PhD students trying to solve the world. Okay, so what I'm going to talk about today it was summarized here in these 5 things. I will define the problem. I will define then the splitting schemes and more specifically Strang splitting schemes and some results and simulation studies. Okay, so if we just look at the second order SD, we can define it as equation 1. And here psi is a standard white noise, and we have some x, that is state variable. We have some drift f, and gamma in this case is a diffusion parameter. And what we want to do, we want to assume that f is nonlinear. Moreover, it's one-side Lipschitz, so we are not assuming globally Lipschitz case, which is quite restrictive, but we are assuming this one-side Lipschitz, and this also can be relaxed. But the point here is that we are working under nonlinear setup, and I would just mention this good quote that is saying that nonlinearity is what gives us job. So everything is solved in the linear case. That's why we work in the nonlinear case. And so if we rewrite the equation 1 as by introducing this auxiliary velocity variable, we get equation 2. So now we work in the first order stochastic differential equation setup with double the amount of state variables. And here we will call x smooth coordinates and v rough coordinates. This is because the noise propagates only, it enters only on the velocity coordinate and then propagates on x through v. And the goal is to estimate parameters beta and gamma from the discrete observations. And now we can also slightly rewrite the setup and concatenate x and b such that we have new variables, variable y, and now a new drift f tilde and diffusion matrix sigma sigma transpose. And then everything can be seen as this first order stochastic differential equation given in equation 3. The problems are we don't have actually y, we only observe x. So we have partial observation, and sigma sigma transpose is singular. Hypoelliptic term means that we still have density, we still have everything smooth for y, but sigma sigma transpose is a singular, which is a problem for most standard statistical tools. And here I'm just showing you one toy example. So I'm not, I don't have real data or any like real problem to solve at this moment, but this is just a specific toy example. It's called Janssen-Reed model. It's used for neural activity. And it has these 12 parameters that are red that we want to estimate. And this is one trajectory of this. So what we actually, under this setup, what we observe are x0 to x2. Okay, so now let's see what the strength splitting is. We can rewrite the drift f as a linear part, which here in equation 4, I call it ay minus ab, and everything else, which is the nonlinear part. And note that we can always do this as soon as we choose a and b, the n is automatically determined as f minus that. And we now look at these sub-SDs that I call them in equation 5 and 6. So we completely independently solve equation 5 and equation 6. And equation 5 is just the linear part, and equation 6 is non-linear part. And note that 5 is the stochastic differential equations, while 6 is a nonlinear ODE. And the solution for 5 is known. We know it, and it has a known solution. So it's not a coincidence that we choose it, to split like this. Obviously, we can choose A, B, and N in different ways, infinitely many ways. But all the asymptotic results hold for any choice of these hyperparameters, if you want. And so the solutions of these two, first one is the Ornstein-Uhlenbeck process. This is just how we can write it. So the solution to y1 is given by this phi h1, which is just a vector flow. So if we are in one point, which is one y tk minus 1, we can go to y tk given equation 7. And then we have this Gaussian random variable, which is psi tilde. And we know the distribution, we know the covariance for psi. So this is all right. And then we also, given the regularity assumptions, we also know that there exists a unique solution F tilde, which is the nonlinear solution. And this nonlinear solution can be analytic, but it can be, we need some numerical tools to find it. So it's not explicit in a closed form, but it's not really important as long as you can approximate it good enough. I think until order 2, this is all valid. And then the splitting schemes are actually using these independent solutions phi h1 and phi h2, and we compose them in order to obtain the approximation for the solution of the starting SD. And we can do that again in many different ways, infinitely many, but we focus on this one, which we call the strength splitting. So basically we choose to compose these solutions such that we go halfway in one direction, then full way in another, and then halfway in the first direction again. And this is illustrated here in this figure 2. And again, this is not the unique way to do it, and there are many other ways. This is the simplest enough such that the results are good enough. Okay. And if we still assume that y is fully observed, so we have both x and v, we can construct the estimator. And how do we do this? So this is a specific Strang approximation for our beginning SD, and it's given like this. So basically, the only randomness here comes from psi, which is Gaussian. So this is Gaussian plus something. So it's still Gaussian, and then we have a nonlinear transformation. So we can use change of variables to get this maximum likelihood estimator. And note that it looks like a Gaussian maximum likelihood because it's a nonlinear transformation of Gaussian, but it has this additional term log determinant of derivative. So it's important to remember for later this the last term, so in the last row, we have some standard like Gaussian likelihood, more or less. And so basically the first term is what we will have, we will work later with. So it will have some covariance that will cancel out with this omega -1 here. Okay, so what we did here, first we try to solve the hypoelliptic problem. And this is one of the reasons why we are using strength splitting. Basically, Euler-Maruyama, which is the standard state-of-the-art, the simplest way to do statistics for SDEs, it doesn't work. And it doesn't work because the diffusion matrix sigma transpose is not invertible. And then what is done under this setup, in this paper, Samson and they used the Euler-Maruyama only on RAF equations. So we have both dx and dv, so they completely ignore the equations dx. And then there is no singularity anymore. So this is how they constructed their estimator. We can, with strength splitting, we can use the full equations, full model. We can use both x and y. And we can also do the same thing, what they did, and use only the rough equations. And we proved that both of these ways are consistent and asymptotically normal with the efficient covariance. And then if we go back to the realistic setup, we don't observe the velocity. We can approximate it with the forward difference approximation. This is not the only approximation. We can do some others, but this is also what's done. So what we want to eventually do is compare with other approximations and see how this influences the results. But for now, we are using this forward difference. And also, I think mostly for proofs, is that y is a Markov process. So it's a solution to our SD. But if we only have x, this is not a Markov process, which means that all the proofs are much more involved. But this doesn't change the results. What does change the result is that approximating velocity leads to a consistent estimator for diffusion matrix gamma transpose. And why is this the case? This is what I tried to hint at before. If we look at the covariance of terms in the likelihood or objective function, we see that this is the approximation, and it's a block matrix here. And what I want you to see is that we have some orders of h, and this is standard that the first part is h power 3, the last part is h, which means that the rough coordinates have much bigger noise than the smooth coordinates. But the more important point is that if we assume that everything is observed, so y is observed, b is observed, then these two things match and they cancel out, which is good. But if we approximated velocity with the forward difference, then we don't get the exactly same covariance matrix. And basically this will not cancel out anymore, which leads to inconsistent estimator for diffusion matrix gamma transpose. And again, what I mentioned before, if we use different approximations, these results will be different, but they will always be inconsistent with some different coefficients. And how we solve this, so here I'm showing the Euler-Maruyama estimator, which is the easiest one, right? And we see that in this paper from 2012, they add these 2/3 in front of the first term, and this term will fix consistency problem, but now we are losing efficiency because of it. And it's also important to see that the only inconsistent estimator, as I mentioned here, is gamma gamma transpose. So the drift estimator was not inconsistent under this setup. So adding this coefficient in the first term will not change the consistency of the drift parameter, since the first term doesn't have the drift inside. So yeah, this is important. And then if we go back to our setup, which is a Strang estimator, as I already pointed out, we cannot now just add 2/3 here. And the reason for that is because now we don't have gamma gamma transpose in the first term, but we have some omega. And this omega depends both on drift and diffusion parameters. So this will fix the inconsistency of the diffusion parameters, but will create inconsistency in the drift parameter. So the solution will be to change omega as well. And by adapting it to this, will actually provide consistency for both parameters. Still, the inefficiency hold. So we don't have the free lunch for both Euler-Maruyama or Strang estimator because we actually don't observe everything. So by approximating some unobserved variables, we lose on efficiency. And here I'll briefly show the simulation study. It's still a toy example. It's probably not the best one to work with, but it's something that was previously done. So I'll just go through it. What we do, we use Euler-Maruyama to simulate with super small step size, and then we subsample to increase the step size and to decrease the sampling error. And we perform 100 Monte Carlo simulations. And also one innovative approach, if you want, is to use automatic differentiation in R, which is not that common. There is no R package for automatic differentiation. It's either in C++ or in Stan or some other languages. So this package is Torch. It comes from PyTorch. So if you work in PyTorch, it's exactly the same, and it's implemented in C++, and there is a wrapper for R. So we use the torch for automatic differentiation, and then we use this resilient backpropagation algorithm to find the parameters. And then we chose this splitting for A and N under the Janssen-Reed model, which is again not uniquely defined. And later on, we realized that in the final sample size, this is probably not the optimal splitting. So there are much better ones. But this is what we did. It's the most obvious one to do. And it's a very simple to solve. If you look at the nonlinear part here, the first three coordinates will always be 0 due to the setup that we started with. But here we can have some more complicated functions. Now, in this case, everything is very trivial because there are no x3, x4, and x5 in these last three rows. So everything is constant, basically. And we can solve this in a second. And these are the results. On the y-axis, we are looking at the absolute relative mean square error. Everything is rescaled such that the 0 is the best. And yeah, so we have these 12 parameters. The reason, for example, why sigma 3 and sigma 5 are really bad is because in this concrete model, we chose, for example, sigma 4 to be 2000 and sigma 3 to be 0.001. So we already started with hypoelliptic case where sigmas are some sigmas are zero, and then we also have two sigmas that are almost zero. So this is one of the reasons why this toe example is not the best. But still, we can see that the orange curves are almost always better than the green ones, and this is what we proposed. There is this problem with B, which probably comes from the fact that we didn't split in the most optimal way. But yeah, so this is going to be investigated. And the take-home messages I want you to have. So if we start with the second order stochastic differential equation, and if you want to work with them as first order stochastic differential equation, we will always have these two problems of hyperellipticity and partial observation. The original Euler-Maruyama doesn't work because sigma transpose is singular. We can modify it. Strang splitting is an intuitive way of doing this approximation. It's very fast, very effective. I also put here for hypoelliptic problems, but also if you don't have a hypoelliptic SD, we have the first paper working in this first order SDs, and we show that Strang is better than other state of the art. And if we have this partial observation case, then we need some correcting terms which will decrease efficiency. And in simulation study, we see that Strang usually outperforms Euler-Maruyama. And then this is the first paper that is not working with the second order SDs. This is the current project. But in this paper, you can see Strang compared to other methods and not only Euler-Maruyama. And that's all. Thank you.
Okay. I don't know how it clapped, but like this. Okay. Okay. Thanks, Predrag. So we have time for maybe one or two quick questions. Yeah, Zhikica. Or sorry if I pronounced not correctly. Yeah.
Am I audible? Can you hear me?
More or less, yeah.
Okay, great. I have just a short question, maybe two. Okay, first thing, have you considered any financial applications? Because SDs are commonly used in finance, for example, in option pricing. And the other question is, what happens asymptotically? Because you said a Strang estimator outperforms EM in the final sample setup. Have you investigated the asymptotic behavior of your estimator? Thank you very much.
Thank you, Zhikica. Yeah, so for the first question, we were actually considering, we were just talking, so it's still an idea to do some housing market pricing. Because basically, if you want to do financial SDs, people are really more interested in, I don't know, prediction and not really in understanding the underlying dynamics. So you don't really want to make your drift as best as possible, but you just want to have a good estimator overall. So there are different methods for financial data. But yeah, if you want to explain some phenomenon like a crash of housing market, for example, then maybe this method would work. So this is what we were considering. And the second question, so basically all of these methods asymptotically work, and they work in the more or less same conditions. So as long as you have sample size that goes to infinity and time frame, time window goes to infinity, and then the discretization steps goes to zero, you have asymptotical results. And for Euler-Maruyama and for Strang and for other methods, it's always the same. So they all work amazing when h is super small, but as soon as h becomes a little bit larger, Euler-Maruyama fails, especially in the diffusion parameters.
Okay, thanks. I think Andre raised hand.
Okay, just shortly, it was a very interesting presentation related to the SDE. Is there any result on extension? Is it possible, I mean, for which SDEs is the scheme applicable, and could it be extended to SPDE as well, to the partial differential equations in general? Thanks.
So basically, the only restrictive assumption for now is that we assume this additive noise, but we are also working on that. So here I have gamma additive. We have some ideas how to generalize that. So in theory, this should work for most of SDs. Also, where in the first paper we worked with the Lorentz system, which is not it's not Lipschitz, it's not one-side Lipschitz, and it still gives results. So this is checked. But for SPDs, I think so. The splitting schemes come from the ODs, and I'm sure other people applied it for PDs. So it's applied to PDs and it's applied to SDs. So I think it can be applied for SPDs as well.
Okay, thanks.
Okay, and so now very short by Kima.
Yeah, hello. If you don't have time, I can put it on chat. I don't mind if we don't have the time.
I don't know, Andre, should we move on or?
Let's allow it. So please, Kim.
Okay, you're allowed to ask a question.
Congratulations for the presentation. I have a very general question. Strong estimator, at least in my eyes, the formulas are a little bit more complicated than other estimations. So can that make its implementation like more challenging in different areas? What are some disadvantages when you're using this estimator?
Yeah, so it's challenging in a sense that you need the solution to this nonlinear OD. As long as you have it, it's very simple to implement. It's like I don't know, 10 lines of code.
Is it easy to have it?
In most of the cases that I worked, it is easy. It's not super hard. But even though if you have some already implemented some nonlinear OD schemes, I don't know, Kuta or whatever that you prefer, as long as it's already implemented, the implementation shouldn't be a problem. Like, okay, now we are still working with this. We plan to do a package. So if you start from scratch yourself, it will be probably challenging, but it should be more or less quite trivial and straightforward.